All right, 1.2 notes. 1.2, we're going to be analyzing graphs of functions. So it just starts by talking about graphs in general. X is the directed distance from the y-axis, or y is the distance from the x-axis. Second page talks about domain and range. It doesn't really go into explaining domain and range, but just jumps right into the first example. So domain, we know, is the x values of the graph. So of our graph here, our domain would be from what to what? What do you think? So domain and range always go from smallest to largest. So domain, we're talking about the smallest x value that our graph has. So what's our smallest x value that our graph touches or goes to? -1. And it's a closed circle, so it'd be bracket -1. What's the largest x value that our graph has? 5. And since 5 has an open circle, it'd get a parentheses. I'm going to jump to C and let's do the range. So range, we're talking about y values. And again, we go from smallest to largest. So what's our smallest y value that our graph has? If we start at the bottom and go to the top, what's the first y value that our graph has down at the bottom? -3. Awesome. It's a closed circle, so we'd put bracket -3. What's the largest y value that our graph touches? 3. And again, that's a closed circle, so it'd be a bracket. Any questions on domain and range? All right, next we're going to evaluate the values. So at f of -1, the number inside the parentheses tells us what x value we're going to. So we're going to go to where x is -1. We want to see what's our y value when x is -1. 1. Awesome. So f of -1, I'll write it on the side over here, is 1. Next, let's find f of 2. So we're looking for where x value is 2. What's our y value at 2? -3. Perfect. Any questions here? Next page talks about the vertical line test. So I kind of mentioned this a little bit yesterday. We do the vertical line test to determine if a graph is a function or not. It is the graph of a function. You want to be able to put a vertical line on any part of your graph to determine if it's a function or not. And if your graph touches 2 points of the vertical line at once, it would not be a function. So if I had a graph like, we'll say something like this. If I put a vertical line down any point of this graph, it only touches one part of the graph at a time. So this would be a function. If I had a graph like this, that was a circle, would this pass the vertical line test? No, it touches at 2 points on our vertical line, so this would be not a function. There's a couple more examples on the next pages. So vertical line test says a set of points in a coordinate plane is the graph of y as a function of x if and only if no vertical line intersects the graph at more than 1 point. So it can only touch the graph at 1 point at a time. So in example 2, we're going to use the vertical line test to determine whether the graph is a function. Kind of already did it for us, but in A, is this a function? No, it touches the vertical line at 2 points. So this would be not a function. What about for B? Is there any point of our graph that touches a vertical line at 2 spots? Nope. So is this a function? Yes. All right, what do we think for C? Any point of our graph that touches at 2 points? Nope, so is this a vertical line, or is this a function? Yes, it passes the vertical line test. It is a function. What do we think for D? So we kind of have to be careful here. We've got almost a point that overlaps, but one of them's a closed circle and one's an open circle. So does it touch our graph at 2 points? No. So what do we think? Is this a function? Yes, it's a function. Because we have a closed circle and an open circle. If these were both closed circles, then it would touch at 2 points. It's not a function. Next, we're going to talk about zeros of a function. So finding the zeros of a function helps us graph our function. The zeros are the x-intercepts. It's where we cross the x-axis. So if I found the zeros of my function, that's going to be the points on my graph where I cross the x-axis. Finding the zeros. Finding the zeros is the same thing as finding the solutions. And typically, if it's something that we have to factor, it's like finding the factors too. It's just solving. We're going to make y 0. You make f of x 0, and you just solve. So let's practice finding the zeros in example 3. So in A, we're going to make f of x 0, and we solve. How do we solve something like this? What would we do? We want to factor. So to solve, we're going to factor. Here, since our leading coefficient's not 1, I'm going to factor by multiplying the first times last. So you can factor however you want to for this. This is how I factor because I find it the easiest, but I know that we've learned different ways on how to factor. So factor it however you feel comfortable. So 3 times negative 10 would be negative 30. What are 2 factors of negative 30 that add to 1? So 6 and negative 5, perfect. So we have x plus 6 and x minus 5. If I start by multiplying the first times last, I have to remember to go back in and divide by the first. So I'm going to divide both of my numbers by that first term, by the leading coefficient. Divide if you can, so simplify if you can. This simplifies to x plus 2. If it doesn't simplify, move it in front of the x. So this would be 3x minus 5. From here, we're solving, so we're just going to set each piece equal to 0. So what does x equal? Negative 2 and 5 over 3. Awesome. So those would be our 2 solutions. If I were to graph this function, I'm going to cross the x-axis at negative 2 and 5 over 3, which would be a little bit less than 2. And then if we remember, what does an x squared graph look like? A parabola. It's U-shaped. Would our parabola open up or open down? What do we think here? It opens up because it's a positive a. Our leading coefficient was positive. So our graph would look something like this. This is just a rough sketch of our graph. We could make it more exact by finding a y-intercept, but this would be a general idea of how our graph looks like. Let's do B. So to find the zeros, we're going to make g of x 0. We changed the y to be 0. So 0 equals the square root of 10 minus x squared. How would we solve? What's the first step? Square both sides. So 0 squared would be 0 equals 10 minus x squared. What's next? I know you guys know how to do this. You're just asleep. X squared is equal to 10. Then what? Square root both sides. So what does x equal? Awesome. Plus or minus square root 10. Any questions here? Awesome. For C, how would we find the zeros? If I make this 0, what would I do to solve for t here? You can. If we multiplied the left side by t plus 5, what's 0 times t plus 5? 0. It just goes away. All you need to do when you have a fraction is set the numerator equal to 0. Because if our numerator is 0, it doesn't matter what our denominator is. If I have 0 over 1,000,000, what would this equal? 0. So all we care about is the top. So yes, you can think about it that way where you multiply both sides by the denominator to get rid of it, but that's one step extra that you don't really need to do. We can just set the top equal to 0. So 0 equals 2t minus 3. Add 3. And divide by 2. So t equals what? Thank you. 3 over 2. Next, we're going to talk about increasing and decreasing intervals. So we have increasing, decreasing, and constant. Just like how you read a sentence going from left to right, we read a graph going from left to right. So I like to think about it. If I was walking along my graph, I always start at the left. Read a graph going from left to right. So we always start at the left. If I was walking along my graph, I'm walking downhill, so I'd be decreasing. Then here I change to constant. Constant's going to be a flat line. And then at 2, we change to walking uphill, so we'd be increasing. For intervals of increasing, decreasing, and constant, you're always going to use parentheses. And it is always the x values. So when you're talking about your intervals here of where you're increasing, decreasing, and constant, you're always looking at the x values. And you're always using parentheses because you can't be both increasing and decreasing at the same time. So we always use parentheses. Next page just talks about the formal definition of increasing, decreasing, and constant. We're going to go to example 4. So I'm going to start at the left side of my graph here. Would I be walking uphill or downhill? Uphill. Is there a point where we change from walking uphill? No. So we'd be increasing from where to where? Let's pretend that these have arrows. Awesome. We'd be increasing from negative infinity to positive infinity. If they had closed circles or open circles, if it ended, it'd be from negative 1 to 1. Now let's look at our next graph. So I'm going to start at the left side. Again, we're going to pretend that these have arrows. So I'd be walking uphill until where? Until negative 1. Perfect. So I'm going to put parentheses here. Where do we change again? Then we start walking downhill. Where would we change from decreasing? Where do we stop decreasing? At 1. So I'm going to put parentheses here, and then we go to infinity. This would be negative infinity. So let's talk about our intervals. I'm increasing from where to where? Negative infinity to negative 1. Perfect. Anywhere else? From 1 to positive infinity. Awesome. Now I'm also decreasing from where to where? From negative 1 to positive 1. Perfect. Am I constant anywhere? No. Questions here? All right, for C, we're going to pretend that these have arrows. The left side of my graph is negative infinity. The right side goes to infinity. So I like to put kind of parentheses on my x-axis where my intervals change. So I see that I'm going uphill until here. So I'm going to put parentheses, then we're constant until here, and then we're going down. So I like to put the parentheses to keep my eyes on the x-axis so I know which intervals I'm looking at, and we're only talking about the x values. So I'm increasing from where to where? Negative infinity to 0. Awesome. And then where are we decreasing? To positive infinity. Perfect. Are we constant anywhere here? It's from 0 to 2. Awesome. So domain range, increasing, decreasing, and constant should be just a review for you guys. Next page talks about relative max and min. So a relative minimum is any kind of valley that we have. So any like lowest point of the graph. A relative maximum would be any hill. It's like not the highest point of the graph, but anywhere where you go from increasing to decreasing would be a relative maximum. So you can have more than one relative maximum. So looking at the next page, any hill that we have, these are relative maximum. Any valley that we have, anywhere where it goes from decreasing to increasing, that is a relative minimum. Now we can also have an absolute max or min. I'll draw a graph here so we can see. Let's say my graph went something like this. So here at the tippy top would be our absolute max. And then at the very bottom would be our absolute min. And then any like valley or any hill, this isn't a very good example of a graph because I've got some sharp terms in there, but this would be a relative min. Here we have a relative max. So you could have more than one relative max or relative min in your graph, but you're only going to have one absolute max or absolute min, which is just going to be the highest point or the lowest point. Next page talks about using a graphing utility. We're not going to use a graphing utility yet to graph, but if we were going to graph this by hand, let's say, what shape of our graph would this have? A parabola. Would the parabola open up or open down? It opens up. It'd be a parabola that opens up. Now this is just a general shape. I don't know if it's on the graph here or not. But at the very lowest point, would this be a relative max or relative min? A relative min. It would also be an absolute minimum because it's going to be the lowest point of our graph. Next page gives us the equation for a linear function. So y equals mx plus b. It talks about this because we're going to be graphing piecewise functions, so it kind of talks about how to graph a line. So when we graph our line, b is your y-intercept, and m is your slope. So on the next page, we're going to sketch the graph of the linear function. We always want to start with our y-intercept. So our y-intercept would be 3. So we're going to cross the y-axis at 3. Put a point there. And then negative 1/2 is our slope. So if I have negative 1 over 2, this would be my rise over run. So I'm going in which direction? Down 1 and which way over? To the right 2. We go down 1 and to the right 2. Always, always double check that your line is consistent with the slope that you have. We see that our slope is negative, so our line needs to be decreasing. can just check the directions that you put your points in to make sure that they're right. Your line's decreasing. My slope is negative. We're good. Example 7, it asks to write a linear function f for which f of 1 is 3 and f of 4 is 0. So here we can turn these into points. Remember, the number in our parentheses is our x. So our x would be 1, and when x is 1, y is 3. And then in our second point here, if x is 4, y is 0. Now we're coming up with an equation of a line. It asks us to write a linear function, so we need an equation for our line. If I'm going to write my line in slope-intercept form, what do I need? I need the slope. How do I find the slope? What's our slope formula? What's on top? X or Y's? Y's. Y2 minus Y1 over X2 minus X1. So this is our slope formula. I'm going to label my points X1, Y1, X2, Y2. So 0 minus 3 over 4 minus 1 be negative 3 over 3. So our slope is negative 1. So we have our slope. What else do we need? Our y-intercept. We need our b. You can find your b either by plugging it into point slope form, or you can plug it into your slope intercept form and solve for b. Either way works. So I'll plug it into, I'll do slope intercept form here. So I'm going to use my point that's given. 3 is equal to, our slope is negative 1 times x, which is 1, plus b. So 3 equals negative 1 plus b. B equals 4. So if we're writing our equation, we have y equals what? Negative 1x, or we could just say negative x plus 4. All right, we're going to stop here for today. We'll do the rest of the notes tomorrow. The homework will be due Monday. So you guys can start the homework. You can do most of it today. There's a few graphing questions. Tomorrow we're going to talk about step and piecewise functions, so graphing them, and even an odd function. So that's kind of the end of the homework, the last few questions. So you can definitely start the homework. Let me know if you have questions from the homework.